Hi, my name is Albert Dunford, and in this tutorial video we are going to do a boost with peak current mode control. So let's get started. We're going to go from 100 volts to about 300 volts over here, and we will basically run a simulation here in open loop to kind of figure out what we're dealing with. So the things that we're interested in looking at is making sure we're getting to around 300 volts here. I don't really care how precise this is at this moment. We'll implement a controller and that'll deal with that a little bit later on, as long as we're in the neighborhood. Look at the current through the inductor. Also, we'll pull up the current through the MOSFET. And those are the things that we are interested in. Let's kind of zoom in over at steady state here, see what we've got. We just need a few cycles. So we've got, oh, and I don't have my, oh, this is just the switching. We need also the current through the MOSFET. Okay, so we're going to do peak current mode control. So we want to basically turn the switch off whenever we hit the peak current. So we're going to be switching at 100 kilohertz, so the switching speed will remain the same. We can see we've got about 15 amps of ripple on the inductor here. We've got the current flowing through the MOSFET down here, and we can see that the inductor and MOSFET rising edges are the same. So what we're going to be doing is actually controlling the current and sensing the current on the MOSFET, and then using that for our control scheme. And then we'll do an outer voltage loop as well. So what we need to do is we need to turn the switch on and then turn it off. We just zoom on like one cycle just to really hammer this point home. So we want to turn the switch on, and then we want to turn it off when we hit our peak current. So once we hit the peak current, we want to switch that thing off, and then basically switch back on again at the 100K point. So this off switching point will be variable. This on point will be constant. And then that'll kind of get us where we need to go. So first things first is let's set up that peak current mode control. So to do that, we're going to need to grab a flip-flop. We'll grab the set reset flip-flop down here. We're going to grab a comparator. We're going to compare versus a reference. We pull back up the, we're going to go to 30 amps here. So we'll change this to 30 amps. Previously, this was just deriving a constant duty cycle of 70%. We need the current here, IFET. We'll pull this over. Okay, and then, so what this is going to do is once IFET is equal to or greater than the negative input, this will toggle high. And so what we're going to do, so we'll look at help here. So we'll go with edge triggered. So that's opposite of 0. And so once it toggles high, we want it to switch off. So if we use this set option here as the input, if we toggle high, we want it to switch off, which means we actually, if we use the QN here, we can, the negative output, we'll get the action we want. So we can reset it and toggle it high, and then we can set it and toggle it low. So let's set that up. Okay, so we're going to use the negative action here, wire that in, and we're going to set this, and then we're going to reset it at our 100K time period. We're going to go to 100K. We need to drive a relatively small duty cycle here because that's that'll drive our minimum possible duty cycle. And this is essentially everything we need to do here. Okay, so we've got our peak current mode control action set up here. So this will toggle the reset for us. And let's run this and see what happens. And if you're familiar with peak current mode control, you might already know what's going to happen. And it looks like this isn't going to work. This is not, our voltage has collapsed. Our current is a short circuit, so this is 10,000 amps. Nothing is working here. Nothing is working properly. So to kind of understand what's happening, let's put this into free run mode, and let's drop this peak reference down a little bit. Let me try and just move that here. We'll change this to 15, and we'll ramp up the peak reference, and then we can kind of look at what's happening. So this is going to be our free run mode, which is kind of like a test bench setup. So we can run this, and we can take a little peek here at the currents, and hopefully I can see the issue to go. Okay. So I've changed it to 10 amps here. Let's have a look at what the output voltage here is just under 100 volts per division, so just under 200 volts. The peak reference is 10 amps. So this one is the current through the FET, and this one is the, let's just zoom in a little bit, and this one is the voltage, output voltage. I'll AC couple this and auto scale it so that we can have a look at the ripple on the DC bus there. So what we're going to do is slowly increase the peak reference here. So there's 11 amps, 12 amps, 13 amps, 14 amps, and we can see, let me just put a trigger on here. We're running into issues. So this is sub-harmonic oscillation. And this happens in peak current mode control when we start to get to duty cycles above 50%. And so that's why our converter didn't work right away when we set that peak reference up at 30, because we can't actually control it at that point. We need to modify the circuit to accomplish that. So as we go up in reference here, we can see this short double pulse thing and this extra wiggle waggle. I'll call it technical terms here in the DC bus voltage. As we keep on going up, we can see that this merged over, and now we're switching at 50 kilohertz. If we keep going here, we'll just end up at a short circuit. So that's what happened. So let me just stop the simulation. Now, what are we going to do? So what the proposed solution is, in the known solution, is to actually add a bit of slope compensation to this, to the reference here. I'm not going to get into the technical details of why. You can read up on that yourself. Okay, so what we're going to do is we're going to introduce a slope into here, and that is going to be set up this way. So we're going to set up a sawtooth waveform. And it's going to basically help stabilize the peak reference and let it return to its proper value at the end of each cycle. So this is going to be a sawtooth waveform. This amplitude, what is this going to be? That's the main question. We're adding a sawtooth at 100K. What should that amplitude be? Well, let's just disable this quickly. Okay, so we'll run this back in open loop with just a fixed duty cycle, and we'll have a little look at what we're dealing with here. Okay, so I'll go back out to steady state. Okay, so what we care about is the slopes of the current. And what we need to do, actually, is add in a slope that has the same slope as the downslope here on the current, on the inductor there. So we're going to add this in. And how to do that, we'll just measure this. So we'll just grab just before and just after here. And that is, I'll just move that right there. Let me pull up the calculator. So we've got our cursors measuring the rise, the fall here. And we're going to look at the delta here. So the delta on the current is 13.265. 13.265. And that, the fall time is 2.849 micro. 2.849 micro. So that's the slope. And we're going to add that slope in over a period of from a 100 kilohertz period. And so that's going to be 10 microseconds. So we'll add that in. And this is the number that we need to add in. So it doesn't have to be a huge number of sig figs there. So 46.56 is going to be good enough. Come over here, and we're going to put that in. So that's what oh, no, that was going to be 1. This is the wrong one. We want to put it over here. There we go, 46.56. Let's disable this guy again, enable this, all these bits up, and hopefully we should be able to get to a peak reference that allows us to drive past that subharmonic oscillation and give us our 300 volts on the output here. So let's run it again. So we were having issues previously, and we'll start from that lower value, whatever it was. I think it was 10 amps the first time. We'll run again here, pull up the current. So we're stable. Let's put this back onto DC. So we want to get to 300 amps, 300 volts on the output. So we'll just increase the reference here until we get to 300. Okay, so we've got our 300 volts, and there's lots of headroom here with regards to current. We just need to be aware of what the limit is for our slope compensation that we've added. And so that was, if we zoom back up again and wait for it to go into sub-harmonic oscillation again. Up. Let's see where it kicks out. It was right around here. There it was. Okay, it's stable there. So basically what might be a good idea is to put in a limit before we forget and say, okay, we're not going to go any higher than 130. Let's push this back to 50, 55. Let's rerun. Close these out, and we should be nice and stable now, and we are. Okay, so we got to 300 volts on the DC bus, and what we're going to do now is close the loop. So we're going to figure out the nice thing with PSIM now is we're going to be able to introduce a perturbation into the current reference and pick up the action over here on the DC bus voltage. So just to kind of give you a preview of what that will look like, we'll add this in. So let's push a perturbation in here. Let's do 10. Do this at, say, 2K. And run this simulation again. You can see there's a little ripple there. You can see there's a ripple here on the current. Let's just quickly zoom in here. So you can see we've got, we'll scale this up. So I've introduced a ripple at 2K. And if we look at it, what's happening, we can see that we've got peak to peak. So there's our 2K ripple. And what's PCM going to do is it's going to do a time domain simulation. It's going to inject those frequencies, and then we're going to do a phase and gain comparison at the DC bus voltage level. And then we're going to use that as our open loop transfer function, and we will close the loop. So we'll come back when I've got all that set up. Okay, I've got the AC sweep set up down on the bottom here, and I've got our AC sweep probe set up over here. The settings I'm using, 20 milli for steady state time. So this was based on how long this converter needed to hit steady state at. A source amplitude of 10. So when we look at the Bode plot, we'll see that there's quite a bit of attenuation and not all that much gain in the open loop system. So that's why we've got this set up here. Essentially, we need a little bit more signal in order to measure what's happening, and then I'm going from 50 to 25 kilohertz with 30 points. And we're VSign 1, so we're controlling this source right here. These numbers won't mean anything during the AC sweep. And so we're doing a comparison versus a perturbation in the current reference versus the output voltage. So we'll run this and see what happens. So here's our Bode plot, and as I said, there's quite a bit of attenuation in the system, so that's why I ended up with a larger perturbations amplitude. And what we're going to do now is bring this into SmartCtrl. Okay, so in SmartCtrl, I'm going to click Import a Frequency Response. We'll do Voltage Mode Control, hit OK. 100K, we're going to do 300 volts on the output. We'll grab that file, boost PCMC.FRA, hit open, hit OK. This other window pops up, sensor. I like to set my references to 1. So we'll go from 300 volts, and that'll be a reference of 1. So we need an attenuation of our voltage sensor of 3.33 milli. And then a compensator, we'll just do a PI. We could do a type 2 if you were keen, but we'll just do this. So this, what I'm setting up here is basically a 0 to 100% reference. So this is sort of everything's going to be per unit. This is going to defining a sawtooth waveform. So just a simple ramp from 0 to 100%. If you start putting in different numbers here, you're going to start getting different gains into the system, which can be difficult to hunt down. And then we'll hit set. And then we'll just pick an operating point. And then we're off to the races. Okay, so this is SmartCtrl. This little red dot is my operating point. So if I cruise this around in here, we can find a stable operating point. So say we don't want much overshoot. We can go give ourselves a decent amount of phase margin. Cross frequency, say like 2K, something like that. Green line is the open loop transfer function. That's what we just generated from PSIM. The pink line is our loop gain transfer function. So this would give us our DC bus gain, our gain at DC, our cross frequency, and our phase margin. And this looks to be pretty good. So what we'll do, and these are the numbers we're going to use here for our PI controller. So these are the numbers we're going to bring over into PSIM. Okay, so let's grab a PI controller. Let's grab a difference block. Let's grab IFET again. Oh, we need the V output voltage this time, so we'll set up a sensor. Label that V out. Down here, don't forget our gain. So this is the sensor gain that we had, so 1 over 300. Wire this in. We should set up a limiter as well. So this is 130. 0 to 130. And a reference of 1. Wire that in. And then, yeah, this needs to come over here. So we'll disable all this stuff. Actually, I'll just cut this out and put it over here. Move this, slide this up. 130, and these values are from here. So this is going to be 1.928K, and then the next one is 1.42878 milli. Hit OK, and we should hopefully be good to go, unless I've missed something. No, there we go. Okay, let's run. Perfect. So yeah, we are at 300 volts. Everything's nice and stable. There's a decent amount of inrush here. We could add in a ramp if we wanted to, so that we could limit the amount of inrush current here. Let's just let's also take a little peek at this IREF during simulation as well. So let's have a little look at what happens here with the reference current during simulation. So this is the interesting bit of the simulation. And let's add IREF. Right, so we're limited at maximum, and then we see the control kick in. Yeah, so that's basically how we would set this up. So I'll set up a ramp limit now. It's relatively straightforward to do. Okay, so I've got my ramp set up here. How I do that is I just set up an integrator here, and I've got a limit set on that of 300. And then I've got a little math block here, and I've just got some conditional logic defined. So if x1's the top input is greater than the second input x2, we should use x2. And then if not, we'll use x1. So during startup, this x1 is going to be smaller than x2 because x2 will be up at the rail. And so what we'll do then is it'll use this ramp up until the ramp exceeds that of the controller, and then this ramp will end up at like 300, which is much, much greater than this. So it'll just continue to use the X2 input after the fact. So we can run this now, and this will show us, we'll see our little ramp, and then we've got our control kick in. We can stop that, that's probably long enough. So where's the output voltage? So a little bit of a different ramp upgrade there, and then look at the current and IL1, and yeah, IRef, let's have a look at that. And so we can see that ramping up for reference current, and then we hit the maximum value there, and then we go back in. So limiting this other inrush current here can't really be done by controlling the duty cycle. We would have to change this. This is the inrush into the capacitor. We would have to change this some other way. So if we look at that, that is the this is the current that we're actively switching. But this current, let's zoom in over here. YA. So yeah, we can't really, we're not really controlling this inrush current here into the cap. But yeah, that's the end of this video. Then I'll do another video where I do a digital controller for the reference that some of the Piccolo processors from Texas Instruments can handle a digital peak current mode control solution, which is interesting because the PWM is triggered by an analog comparator circuit. Obviously, with peak current mode control, we need to have this analog comparison to sense that peak current, but the reference can be supplied by a digital to analog converter from the MCU, and then also with the PCMC, with those processors, that you can add in a slope compensation, so you can set up some interesting triggering and all that kind of stuff to do this kind of thing. Obviously, this is a somewhat simplified approach. If we were really going to implement this, we would probably want to add some filtering in on this current to make sure that on the initial turn on, we don't have a spurious trigger. So let's add some blanking and all that kind of stuff. But the general idea is here. Okay, so that was peak current mode control. We did an open loop. We figured out how much slope compensation we needed. We ended up coming up with where are we here? We ended up coming with what a reference current we needed. Yeah, everything's there. So check back again for more videos. And yeah, the next one I'll do a digital controller with this, and then I'm also going to try and do some videos soon for peak current mode control with other topologies like a bucket converter, potentially a facial full bridge converter. If you have requests of what you'd like to see done next, do let us know in the comments or send us an email, etc. Thanks again for your attention, and do check back again for more videos. Thanks so much. Bye now.